Okay, well, let's go ahead and get started. Welcome everyone to this month's program for the Denver chapter of CRES. Tonight's speaker is Blair Willcox from CurrentTech Energy. You can see the title of his presentation is Decarbonizing, Heating and Manufacturing and Other Medium Temperature Applications. Today's date is May 15th, and we're here at Odell's. I'd like to say a few words about our mission. Our Colorado Renewable Energy Society's mission is to support and create a carbon neutral Colorado powered by 100% renewable energy, to transition Colorado to a new energy economy that is 100% renewable through education, engagement, and creating networking opportunities across all Denver communities. We value renewables, emerging technologies, efficiency, diversity, inclusion, and community. CRES is a statewide, nonpartisan, nonprofit 501c3 membership organization. I also want to take a moment to thank and show some appreciation to some of our corporate sponsors at the gigawatt and megawatt levels. We have the Poudre Valley REA, Vista Engineering Group, Moss Adams, Kelly Government Solutions, Solaris Energy, Platte River Power Authority, and Centon Instruments. Also at the kilowatt level, we have the ARS Solar and Renewable, Standbox Solar, Branch Architecture Studio, Helio, BrightSense, Terranexum, COSA, and the Colorado Green Building Guild. Also want to show some appreciation for Odell's Brewing, which has been so gracious as to offer us this space for free. Their business model aligns with our mission as well. I believe last year they worked to save 1.4 million tons of carbon emissions from their operation, as well as they continuously work to improve the water efficiency. As you know, water is very important to the beer brewing industry, and they're working to improve their efficiency, something we very much appreciate here in Colorado. Here's a word about next month's event for MDCRES. Our speaker is Enrico Bonallari from EMU. That event will be on June 19th at 6:30. You can see the title of his presentation is Deeper, Healthier Electrification, Passive House Retrofits, which is something that will be of great interest, given much of our housing here in Denver is older and maybe needed some updates to bring these homes into alignment with our current low emission goals here in Denver. Now I'm going to turn the event over to our speaker, Blair Willcox. Again, the title of his presentation is Decarbonizing, Heating and Manufacturing and Other Medium Temperature Applications.
So I'm Blair. I've got 17 years of experience. I started doing energy efficiency audits back in the day, transitioned through decarbonization strategies and renewable energy strategies. My last stop, I was focused primarily on large-scale corporate renewables projects. And then really decided that I wanted to focus on scope one, on thermal processes and how we decarbonize them. Because it's an area that I don't think has gotten a lot of attention, a lot of love. And it's a huge source of emissions for the US as well as nationally, or as well as globally. So that end, industry, if we look at the direct emissions from industry, it's about 23%. It's about a quarter of the US emissions. So very similar to what we see from the electric power industry. And there's been a lot of time and a lot of focus on how do we decarbonize electricity, which is great. And frankly, what we're going to talk about a lot of tonight. But industry has gotten not as much of that attention and not as much of that love. And it's always been viewed as this hard to abate sector. And so I want to present some ideas that maybe this isn't as hard to abate as we think it is, particularly when 68% of those emissions and that energy that is used in that sector come from process heating. So it's a really important area that we do spend some time thinking about and working on and decarbonize. So as I've sort of gotten into this space, one of the things that I've seen, and particularly talking to universities, is we have a lot of universities that are turning to hot water systems from steam. And this makes a lot of sense because it's a much more efficient operation to use hot water. However, when you look at the capital expenditures required for this, it always struck me as it's so much money for, I would say, important but not sufficient decarbonization. So today I saw a study that came out from the University of Washington they're looking to spend $1.8 billion on their steam to hot water conversion rate at their campus. So they're spending a tremendous amount of money because they think steam is a dead end, and they are looking to turn to hot water, which is great. It's a super efficient system. It's going to be amazing. But I'm worried not about the University of Washington, who can spend that much money, but for the campuses and for the manufacturers that can't or won't spend that money to decarbonize. And if we can do a lot of the same work for a little bit less money, can we spend that money on more efficient, more useful decarbonization options? Build a lot more renewables, things like that. Because if we replace steam, steam is incredibly energy dense medium. And so we can take steam, put it for heat exchanger, and a very small volume of steam will create a tremendous amount of heat. If we turn that to hot water instead, we need a lot more hot water, a lot more volume. So now all of a sudden we have to replace the heat exchangers, we have to replace the piping, we have to replace the boilers, we have to replace everything basically that touches the steam at all in order to get there. And as a result, we have a tremendous amount of capital investment into changing from steam to hot water. And so my thought is, how do we look at things and find ways to decarbonize the steam instead of necessarily throwing out that whole system? So in my mind, when we think about why was this a hard to abate sector, honestly, at least part of it is due to this. Natural gas is $4.38 to deliver 1 million BTUs to your industrial process or to your campus. Is incredibly cheap. And frankly, that's twice as expensive as it was a year or two ago. Natural gas has gone up a little bit, which helps the economics for everything else. But it has made, the cost of natural gas is super darn cheap. I will contrast that to Europe. If we look to Europe, Europe has had a much more electrification and a lot more work in this area because their natural gas is much more expensive. And their electricity prices are about the same. So as a result, we end up with a better ratio from electricity prices to natural gas prices. So I'll compare that to LCOE, so the levelized cost of energy for a couple other resources, right? So if we look at wind, this is Lazard's numbers. It's about $9 to deliver a megawatt or to deliver 1 million BTUs of energy to your facility. And so it's about twice as much as natural gas. And so obviously that's not going to be an immediate one-for-one easy replacement. There's no financial rationale to do that at this point. So we're going to talk a lot today over the sort of technologies or approaches that might work to bring that cost down and to find ways to make that more comparable to the natural gas price. We're not going to talk too much about other gaseous fuels. We're not going to talk too much about biogas, renewable natural gas, or hydrogen. If you look on here, you can see biogas is hanging out in the middle. So if your facility is right next to a wastewater treatment plant or a landfill that's making biogas, it could be a good option. But broadly, RNG is very expensive. Green hydrogen is even more expensive. These are things that are probably going to be limited in their availability compared to electricity. And so we really view electricity as the decarbonization strategy. I think it's appropriate to think of that way as we move forward, except for very esoteric things that need special treatment. I'll mention two other things here that we're not going to talk about a whole lot, but I think are interesting enough to at least mention. If we think about how steam is utilized in the power industry, there are a couple zero carbon options that are also starting to show up or think about showing up in the next handful of years. So one is deep geothermal. So if you put glycol or whatever working fluid down far enough down into the earth, you can get it to boil and make steam come back up. And this technology is used by Fervo and some other companies that are used to then make steam and run through a turbine. That deep geothermal and that steam that's generated from that can also be used as a direct offtake for a thermal process. And so instead of spinning that turbine, we'll just take that thermal steam off and use that for a thermal process. I think that's a cool, interesting technology that might show up in the next couple of years. Very similar with SMRs. If we have a SMR as part of our overall kind of energy generation systems, we've seen this proposed for a couple industrial parks. Could be an interesting kind of option for generating steam as well as power. Yeah, go ahead.
The numbers in this slide don't seem like they're consistent with the numbers we've been looking at, because we have been seeing that wind and solar is cheaper per unit of energy or per BTU.
Yeah.
So
to
compared to the natural gas. And
yeah, so what I'm showing is that this is 2 to 3 times more expensive than natural gas.
yeah, and that's not the numbers that I'm just wondering why there's a discrepancy, because like over at Jefferson County, the one in Golden, we've been looking at a lot of PowerPoint over there, and the wind and solar is cheaper per unit of energy. And even the tri-state executive had mentioned that in one of his presentations. That was quite a few years ago. That was like 5 years ago, I think.
Yep.
But he had mentioned that if you're getting a bid on a new plant, that it's cheaper to get the wind and the solar per unit of energy than the gas and any of the fossil fuels at this point.
No, that's, yeah.
You still have the cost of retiring the old plants, which is a cost.
And so that's a great question. And so I want to differentiate. The natural gas we're talking about here is direct use natural gas, where we're burning it on site. And so natural gas is cheaper to burn on site than to import energy from the grid. And that's and so essentially, because if you look at a power plant, the power plant efficiency comes into play here. And the power plant efficiency is significantly worse than a boiler efficiency on site, because you're generating electricity compared to heat. And so if you look from like an entropy kind of perspective, it's easier to make heat than it is to make electricity. Does that make sense?
If you had a new campus, a brand new campus, had to build a new boiler.
Yeah.
Work that into the cost. Then her point would be.
I think so. Yeah, and I mean, I think it's different when we're trying to generate electricity from a from a system or not.
Yeah, but for 100 years.
Exactly. Yeah, sorry, that's a good point, that the natural gas here is just the operational cost natural gas, so the incremental cost of an existing boiler. It's a really good point.
Really, that's always a challenge for Lazard and everyone to how do we run numbers.
Exactly, and how do you present it? Because
I look at it and say, where's the unsubsidized natural gas part?
yes,
I want to push that.
Yeah.
So ingrained in our culture.
agreed. No, 100%, 100%, and this is all undelivered as well, except for the natural gas. Yeah, natural gas is also wholesale cost too. So there's a lot of nuance here that is hard to accurately prescribe, and is very dependent, frankly, on the individual space that we're talking about.
You have a decision. Yeah, accurate analysis.
Yeah.
They already bought the boiler.
Exactly. Yeah.
But he's going to show us how to solve it.
I am going to show you how to solve it. So the first technology, right? Again, we have expensive electricity compared to natural gas. Natural gas can generate heat very easily. We have expensive electricity coming in from the grid. How do we smush these two together into a way that makes a viable project? So one way is with heat pumps. Heat pumps, I think everyone is hopefully aware of, takes heat from a source and delivers it to a sink. And so you take, so basically you get more out for what you put in. And so you put electricity in and you get more than that amount of BTUs that's in that electricity bundle out back on the other side as part of the thermal. So you can do these in your house. You can do this, your refrigerator is essentially one of these as well. All refrigeration cycles essentially do this thing. The cool thing is that what we're now starting to see is we are seeing steam generating heat pumps. And so for a long time, you could get 90% of the way to steam. You get 95 Celsius, 90 Celsius hot water, but you couldn't get steam. In the last couple of years, we started seeing some come onto the market that can actually generate steam. So the diagram we have up here is from AtmosZero. They're up in Loveland, Colorado, which is cool that they're very local. They are delivering their first steam generating heat pump to New Belgium Brewery up in Fort Collins. So sort of a wonderful Colorado story. It's great. You should definitely go support them with drinking some beer. But they are basically using an air source to say taking ambient air from Colorado, running it through 2 refrigeration cycles in order to get it to hot enough to generate steam and delivering that steam to the process. A lot of the work in the industrial heat pump space is on, here's my favorite refrigerant, here's your favorite refrigerant. And so there's a lot of that going on for sure. So I think this is the first true air source one that I've seen. There are a lot of other ones that are non-air source and use a waste heat stream from the process. So the picture on the previous slide is of Skyven. They can take any waste heat stream coming off your plant and then upgrade that essentially to generate steam. And it's a really cool technology that takes, rather low-grade heat and heats it up to something that's actually useful. So really cool. And frankly, a really good solution for plants and processes that have unavoidable waste heat streams that coming off them. There are a handful of companies that are making these steam generating heat pumps. The last three, as you go left to right, are US companies. And so this is starting to kind of take off in the US. But again, because of the cost of natural gas being so much cheaper in the US, it has, I think, delayed that process a little bit. And so we see more in Europe and APAC, frankly, than we do in the US right now. And so I'm an engineer, so I had to throw one ridiculously over the top graph on here. And I want to talk about COP. So COP is coefficient of performance. So basically how much heat you get out for the amount of electricity you put in. And so on the axis, on the x-axis here is the lift temperature. So basically, what's the difference in temperature between your source and your sink, and the steam temperature essentially. And so, as you think about it, if you're doing an air source heat pump, you can be down to -10 degrees Fahrenheit, right? And then you're trying to raise it all the way up to 212, 250 degree Fahrenheit. As a huge lift, huge amount of energy that you need to put in there to get that up to steam temperatures. Conversely, if you're trying to do a very small thing, if you're trying to take 200 degree waste heat stream to 250, much smaller delta, much smaller lift, you can do that with a much higher efficiency. And that's frankly why we see a lot of these initial attempts and initial focuses were on using waste heat streams in order to be the source for that heat. And frankly, the same reason we see so much focus on going to hot water was because a water heat pump was always viewed as sort of the answer to decarbonizing heat. And that if you've got 120 degree water going into your plant, that's very easy to make with a heat pump and a very high efficiency, really cool system that can be very efficient. But again, I think what we're seeing, what I'm trying to show here is that we're unlocking, with these air source heat pumps, we're unlocking the ability to make steam at a reasonable efficiency in order to start bringing some of these costs closer to comparable with natural gas.
120 degrees is a high temperature for water, isn't it?
I would say for most heating operations that you're with a central plant, I don't think it's particularly hot. I think there's a variation, right? You can do whatever you need to do in order to make your numbers work. And again, the more heat you can put into these things, the more heat you can deliver. And so that's sort of the challenge, is you have a transition between flow rates, volumes, and temperature.
To really nerd out on the previous slide, are the steam cases usually dual cycle and the water case is single? Do you know? I'm just curious why the curves are a pretty different shape. Seems low.
This shape
seems worse at the low end and actually pretty good at the high end. That's kind of interesting.
Yeah. I don't know.
That's right.
I'd have to go digging further into the paper. Apologies. Yeah. Broadly, I would say again, we also have a lot of these being waste heat streams, and so I think it's not necessarily if it's single or dual, but it can be depending on what your source stream is, right? Exactly. Yep. All right, so just to change numbers up a little bit more anyways, we're gonna now talk 57 cents a therm, which is more than the 35 cents I had on the first slide, because this is the delivered cost. So that includes the wholesale cost, but also the delivery cost for your utility. That's the US average. If we kind of run that through an efficiency of the boiler, we basically need it basically costs about $7 to deliver 1 million BTUs to your facility. If we just take electricity, run it through a resistance heater or boiler, that same amount of electricity would cost $24 based on 8 cents per kilowatt hour industrial average. We start bringing heat pumps into the equation, that's when we can start bringing these costs down. And so we go from $24 if we have a COP of 2, which is essentially what the Atmos system can do. That will bring it down to $12. So still more expensive, but getting closer. And then if we get a COP of 3, which is, again, is a lower lift situation, either a water or a heat recovery kind of situation, we're down to $8. Again, I think we'd say very competitive with natural gas. So that's the left side. If we then look at the right side, this is emissions, and this is based on average US emissions for the grid. So caveats, very, very strong caveats here. This is very strongly going to depend where you are in the US, what's going on, what the generators are in your site or in your grid. And so natural gas is not going to change. That's going to generate 146 pounds of CO2 for 1 million BTUs delivered to your facility. If you then just, again, run that resistance heater, that toaster, that's going to be 227 pounds of CO2 based on grid averages. And so this is not one of the situations where electrification is always a net good from day one. We do need to be smart about where we put these things and how we think about them and how we utilize what's going on. However, again, if we bring the heat pumps in, we can start showing some real emission savings. So we basically, again, can drop that in half with a COP of 2, and then another 50% or whatever to a COP of 3 down to 76 pounds of CO2 for that same delivery of 1 million BTUs. So the process that of how we kind of would look at doing a heat pump is the first step, and again, I'm an energy efficiency engineer back in the day. Efficiency is still important. So let's focus on doing energy efficiency as it makes sense for a potential electrification situation. So lower steam pressure where we can, heat recovery where we can, and then just get on top of O&M. Make sure that we're doing our steam traps, all that good stuff that is part of keeping a good steam system. And frankly, the O&M portion is why a lot of people I've talked to want to get away from steam. They're finding it harder and harder to keep their steam system in a good shape. And so they, from a broader perspective, don't want to keep steam. And I think that's a totally valid reason. If your steam system is just going to pot, like, no reason to keeping that going, and you can, might be time to go to a new generation of system. But for systems that are in good shape or just need a little bit of love, worth, I think, again, considering keeping them. The next kind of decision is, do you want a hybrid situation where you have natural gas and electricity, or do you want a full electric system? There are going to be a couple challenges, right? These are early commercialization, so the CapEx is going to be higher for these steam generating heat pumps. The bigger, I would say a similar importance thing is that we're seeing limitations on how much utility interconnection you can get. Data centers are eating everyone's data load interconnection. And so if you can't get load interconnection, you might be limited quite significantly on how big of a boiler you can build. And similarly, high voltage transformers are, again, in high demand, very long lead times. If you can get allocated 1 or 2, maybe that's how big of a system you're going to build. And then finally, heat pumps are limited by how much capacity they have as source temperatures go down. And so if you're planning for cold startups, if you're planning for when it gets really cold outside, worth thinking about and making sure you have a system that's built in order to supply that required energy. So you got your design all figured out, you install your heat pumps, you then optimize operations to minimize utility costs. A little preview of the rest of our talk is going to be a lot about utility rates and how electricity costs work, because minimizing utility costs is vital to making this as viable as it possibly can be. And so for this kind of design, particularly if you've got a hybrid approach, demand response, things like that can make things very much more cost effective and help the grid out as well. And then the final step, and then again, from a corporate sustainability and renewables kind of perspective, let's look at how do we make sure we were procuring renewables to cover the load for this new electrified process. I don't want to dwell too much on this because I could go on for half an hour on this alone, but there are a number of different ways to procure renewable energy. You can do behind the meter solar, you can buy unbundled RECs just on the market, you can do a corporate VPPA or virtual power purchase agreements. There are a bunch of different ways that are very kind of standardized, I think, for large corporate scope 2 decarbonization efforts. And so we can essentially use the same platform and same pathways that are already sort of fully formed to support decarbonization in this sector once we've electrified. And just to note that it's worth watching where this goes. The Greenhouse Gas Protocol is working through updates right now. Worth understanding where that ends up because things could change quite dramatically as that goes forward. So I did what I'm calling a SWOT. I don't know if it's a real SWOT, but kind of a summary of this technology. On the strengths, it's a known technology. It's known, it's a little bit of a different application though. So things are still sort of shaking up there. And so a weakness is that it's still kind of first, second of a kind. Other strengths, smallest electrical demand of the things we're going to talk about. So using that COP is really helpful to minimize both the size of your electricity transformers you need, as well as your interconnection and things like that. And it can fully replace natural gas today. So you could go to a fully electrified system, have no natural gas on site. You know, there's a lot of value for some of the, corporate reporting, for publicity, things like that. So that can be a very valuable thing to do. As mentioned, we're still trying to get costs down to where natural gas is. Probably hard to get down there in a lot of spaces. So you might have a higher operating cost compared to natural gas. As I said, it's in the early commercialization standpoint. And then because this is theoretically a 24-hour operation, or at least whatever your operation of your facility is, you are going to add demand to the grid during peak times. And that's fine. I mean, I think this is a respectful way to do that, frankly. But it is going to, increase demands on the grid, which is at a hard point right now, frankly. And so just one consideration. I think the opportunity where this is most applicable is, for sites for waste heat. If you have a waste heat stream, it can be a really nice solution. And the Skyvens of the world are working really hard on these MVRs that are going to be able to take that low-grade heat, upgrade it to high-grade heat, and have a lot of value there. They got a loan office, EPA loan office, EIA loan office, Department of Energy loan office, grant to build the first of that one. So looking forward to seeing how that goes. But there's a number of other MVR companies that are doing that as well. And then obviously looking for places where the costs make the most sense. And so lower electricity costs, higher natural gas costs, that can generally help things along. Are there any questions on heat pumps before we move to the next section?
Well, on the waste heat.
Mm-hmm.
So what kinds of processes are you looking at there for the waste heat? And the other thing is it will increase the efficiency of the heat pump. So that's if you're trying to heat and not cool.
Correct. Yeah. So we're talking for this system, or for the kind of the talk broadly is primarily focused on process heat loads. So if you need to put heat into your industrial process to do something to build your piece of your widget, that's and so you have both the winter load and summer load. That's kind of the focus of what we're talking about. And so when you have a waste heat stream, if you've got exhaust from one of these operations, so we see that a lot of ovens have necessary exhaust based on eliminating VOCs and things from the process. That's the main one that I can think of, but there's some other ones depending on it's very process dependent to figure out where those waste heat streams exist.
Okay, so waste heat, it increases the efficiency of the pump for heating.
Exactly.
Heat. Okay. Thank you.
One other example I would have is that we one of my clients, they had a big paint booth, and so They had a tremendous amount of air that would go in and get heated up to ambient conditions and take all the stuff out of the paint booth and exhaust it back out. And we're talking tens and thousands of CFM for this space. It was huge, huge volume. And so again, it was coming out at 70 degrees, so not super hot, but hot enough that it's a lot better than 0 degrees, right? And so by using that heat, you're gonna have a much better COP than you would if you just kind of used ambient air. Any other questions?
Is there any opportunity for high temperature thermal storage to help with the peak demand challenge?
You'll have to hang out for
All right.
for about a minute.
Okay.
Any other questions? All right. So I've titled this second half of this Grid Interactive Solutions. And really what I think we're focusing on here is how do we envision a solution that can actually support the grid, right? Because the grid is very challenged at very discrete times of the day or very discrete portions of the year. When we've got heat waves, when we've got cold snaps, these are times where we really don't want to be taxing the grid. And as we integrate more and more renewables on the grid, how do we use dispatchable loads in such a way that can really absorb the renewable energy that's coming off of those facilities? So we're curtailing an awful lot of renewables right now, just because there's too much renewables coming onto the grid. So if we can have load that can actually just selectively absorb that, we're in a really good situation, both on costs, as well as sort of grid happiness. And so the next kind of section is really focused on how do we absorb just those timeframes and that energy while producing, I think, a good outcome, in my mind, way better than Bitcoin, of decarbonizing these thermal processes. So a quote from Jenny Chase, who is the lead analyst for solar at Bloomberg NEF. She says, by 2030, most countries will have a spot price of 0 during sunny hours. And this was really, I think, I reflected a lot on this, and this was very similar to what I was doing with corporate PPAs. And so essentially my corporation would be buying the output of these solar farms. They would buy it at $40 a megawatt hour, and then they would sell it back into the market at whatever the wholesale price was. And oftentimes, as I was looking at the forward curves of what the projections were, these prices started going down and down and down and down to the point where they were $5, $6 a megawatt hour, which is below the cost that they were paying, certainly below the cost of what it costed to build that plant, but cheap enough that we can replace natural gas with it. And that's when I got kind of really excited about how do we start thinking about this in a way where we can start selectively grabbing that energy and that electricity at those hours to displace natural gas.
That means 0.
Kind of. Well, the wholesale market will go negative. So in Texas, there are plenty of hours where costs on the wholesale market are negative. So essentially, this all comes down to sort of bidding dynamics of how power plants bid into the system. But essentially, if you imagine all solar bidding in at $0 because it doesn't cost them anything to run, they can say basically like, we'll take whatever price you will pay us for this electricity. You then have power plants that can't turn off, because if you have a baseload coal plant or a baseload natural gas plant, they can't turn off. The cost for them to turn off and turn back on are extremely high. And so they're willing to take negative costs, negative dollars to keep generating. And so as you sort of see, as you get into the wholesale market, there are a lot of these weird things that happen that are unintuitive and certainly don't match what we see on the utility bills. We'll talk a lot about sort of this disconnect, I think, between the wholesale market and the utility bill market, or what you see on your utility bills as we move forward. So this is the duck curve. This is sort of this first discussion on what we're seeing, where we have this tremendous amount of solar coming on the grid. And it looks like a duck, kind of. And so this presents an incredible challenge, I think, for the grid operators. I don't envy what they have to do. And I think a lot of some of the pushback they get for renewables is based on the challenges that renewables do present to the grid in a real way. And so if you look on kind of the right-hand side there, we're going from essentially zero demand on these fossil fuel generators to 20 gigawatts over the course of an hour or two. It's a tremendous ramp rate. It's a tremendous thing to take these natural gas plants from nothing to full output during those times. But what I'll say is that does present an opportunity, I think, for off-takers who are cost sensitive and sort of focused and thinking about this in the right way, in a very flexible way. For off-takers, for people who are using electricity, and if you can buy it at low prices during those solar hours, there's some opportunity. I'll just talk about ERCOT here as well. This is Texas, and so if you look at Texas has both a lot of solar and a lot of wind. And so you can see overnight prices are very low. They then kind of spike up in the morning, and then they get really low overnight or during the middle of the day when all the solar shows up, and they get expensive then again in the evening. Like really expensive, frankly. Like there's $200, $175 per megawatt hour. That's more expensive than your electric rate that you're paying at your house. But certainly more expensive than most of the commercial and industrial plants are paying. And so the idea is that if we can grab that really cheap electricity during those solar hours, that really cheap electricity overnight or in the wind hours, and use that for your thermal processes, that's going to start being cost competitive with natural gas. And it's good, the sort of the end point is that this is the dramatic way to decrease costs. Xcel is changing their rates too, much more towards taking that evening peak, because that's where they're seeing it, right? Because they have a lot of wind and a lot of solar as well. So they're seeing evening peaks. And so they're moving from, 1 to 7 to, 5 to 9 now? And so, sorry?
7.
No, they got approved by the PUC.
I thought it was like 3 to 7 or.
It's 3 to 7 right now is peak. They are moving peak to 5 to 9 starting in December or next year. I don't quite know exactly the dates. So they're changing it because they're having the same thing. They're having those peaks in the evening time.
Because between 8 and 9, there's not that much usage, I don't think.
I think there's more than you think there is. There's a lot less solar, and the way wind kind of operates is that it doesn't pick back up until a little bit later. And so basically the roll off of solar until wind picks back up is the most challenging times. This is just broadly a discussion of we should really think about when we use electricity. So this is sort of, I think, wrapped in this idea of how do we use this for thermal processes, but this is, I think, a much broader conversation of how do we do anything energy intensive over the next 30 years. We should be thinking about this.
But if you're charging your car right now at noon with Xcel,
yeah,
I guess it isn't the highest peak, but I guess it's not the second highest peak either, is it?
But if you charge at 1, right? But I'm a little annoyed that Xcel is immediately changing their time of use rates because they should have seen this coming. This isn't new, but again, that's a separate soapbox. All right. So to your point, this is what my Xcel bill looks like. I don't get hourly rates. I don't get things like this. Why is that? There are a couple things to kind of think about, right? So the first thing is that there are a number of what are called organized wholesale electric markets in the U.S. So I talked about ERCOT. That's Texas. There's SPP. There's MISO. There's PJM. These are all areas where electricity has a marketplace to be bought and sold in a transparent fashion. All the gray areas, so the Southeast and really most of the West, has no organized market, and so there's no visibility on how much electricity costs during any particular hour. And so we have this great graph, right? I can tell you exactly how much electricity costs on the wholesale market in Texas at any hour I want because they have this transparent market that will tell us this. In the gray areas, we don't have that. And so utilities are more broadly vertically integrated. They have their own control over their own power plants, as well as their other energy they're buying. They don't have to buy or report on this kind of level. And so step one, if we're looking again to buy that cheap electricity, we're either relying on utility to say, hey, here's an ultra low electricity rate for very particular hours. which does exist but is rare, or two, can we access the wholesale market? Can we access market in one of these organized markets? However, just living in those states is not enough. We then have to get to a spot where we're not behind a utility who has decided in our best interest that they're not going to provide us wholesale market rates. And to be fair to them, you know, the electricity rates, they assume you're not just going to use electricity when it's cheap. You're going to use electricity when it's cheap, but also when it's expensive. And they're also going to have to do a lot of other things on the wholesale market to support your procurement of this energy. You're going to pay capacity charges and things like that. And so they have to basically build a rate that is going to cover them for all these different components. Again, assuming you're not just going to buy it when it's cheap. And so broadly, if we're trying to get wholesale market access, we have to be both in an organized market as well as have retail choice on this, where you can either access the market directly or use a retailer that will provide you these sort of real-time rates. So again, it's a kind of a Venn diagram of finding the right spots to get this done. I don't want to talk too much about this because this is, again, another 30-minute or an hour discussion on what wholesale markets rates include. But broadly, what we're trying to do is buy energy and avoid paying for anything else. Because if we pay for anything else, like transmission or capacity, and to a certain extent as little distribution as we possibly can, we're going to get prices too high to be cost competitive with natural gas. And helpfully, the way that most capacity and most transmission charges work in the wholesale market is that if you don't use electricity during the peak hour, and so in Texas, for example, in transmission, it's the 4 peak hours or the 1 peak hour in each month of the summer. So 4 months total. So June, July, August, or June, July, August, September. If you don't use electricity during that time frame, you don't have to pay any transmission fees at all. Similarly, in PJM, if you got the capacity charge, if you don't use electricity in, it's not 4 CP, I don't know if it's 10 or if it's 6. It doesn't really matter. But if you don't use energy in the peak hour of that month, you don't pay a capacity charge for that. And that's really important because capacity charges have gotten really high in PJM this year. So it's basically doubling people's rates. So worth kind of thinking about this, again, more broadly than just this space, but specifically for this space, we really need to avoid those charges. And again, this doesn't look like my utility. My utility bill has energy, maybe a time of use rate, has demand charge. You know, most C&I customers have a demand charge. And then they've got a bunch of fees on them. If we're trying, again, to put this on a retail utility rate, we need to find both an ultra low rate as well as avoid demand charges. So if the demand charges don't occur during off-peak hours, we can use off-peak hours to use that energy for our thermal processes without triggering a demand charge. These are the kind of things that need to get done in order, again, to drive that price down as far as we can. And I realize that we're talking a lot about very specific utility and cost allocation issues. But I think it makes sense, at least to me, and other people may disagree with this, but it makes sense to me because we're trying to only use electricity when it's essentially unwanted. And so in a sort of grid supporting manner. And so as sort of an idea of allocation of costs and a driver of costs, we're trying to avoid times when the grid is taxed, when generation is taxed. We're trying to use sort of the least desired energy at all. And so I think we should be rewarded with as cheap a rate as we possibly can, because I don't think we're driving any new investment in technology or infrastructure to drive that. So apologies for the long-winded discussion on utility rates. But again, if we can get really cheap electricity to the point where it's 2-3 cents a kilowatt hour, we can be cost competitive with natural gas, even if we use resistance heating. And so using resistance heating, we do some really cool things. One of them is the thing that made me fall in love with this sort of area to work on. I call hot rocks. The geothermal guys are fighting me for who gets to call their stuff hot rocks, but I think my stuff is called hot rocks. This is a Rondo heat battery. So essentially, what they do is they take a resistor, toaster resistance coil and basically run it through a whole bunch of bricks. They heat these bricks up to 1500 degrees Celsius, incredibly hot, over the course of 4 to 6 hours. They then turn it off, and you can generate steam from that heat battery for 24 hours. Obviously, it's got to be sized correctly and things like that, but that's the idea. And so again, you can grab the cheap electricity during the day or overnight, depending on where your grid is, use that to charge this up, and then make steam all day, creating no issues for the grid more broadly. This is really cool. I love it. It does require an incredibly large electrical infrastructure system to support that. And I think, frankly, that's the biggest thing. And as AI data centers and electrical infrastructure. So you need huge switchgear. You need the utility to say, yeah, you can draw a megawatt, or sorry, 10 megawatts, 20 megawatts from our grid at that point. Incredibly large amounts of energy we're talking about to make this happen. But it's very cool. And again, if we have that capacity from the generation and from the grid during underused times, we should use it for benefit here. These guys have one unit in California that's up and running. Discussion I've had with them since then has been most of their stuff is going to Europe, again, because of the spark ratios are better there. And natural gas is more expensive, so it's more cost effective to install those over in Europe. But I think they're so cool. I love them. And I think they are the idea of how we should be thinking about flexible loads in this. These are expensive.
And what is the cost related to building something like this? And the energy is only around for 24 hours, nothing longer.
Yeah, so you would charge it every day. And so it's essentially the same as a lithium ion battery, is sort of conceptually, but it only generates heat and not electricity. And so, but if you're going to use electricity to generate your heat anyways, it all kind of makes sense and works. These are expensive, but they hold a tremendous amount of energy. And so they are saying it's roughly 10% of the cost of lithium ion. Whether or not that's true, I have not gone through the full process.
10% of the cost of
a lithium ion battery.
Oh, okay.
So much cheaper than lithium ion. But
so like if you compared it to hydrogen or just, I don't know,
it's
just any other kind of storage, like battery storage or anything. Yeah.
Sorry.
Just compared to other storage costs, because it's really a storage mechanism.
Correct.
Right?
It's 100% a storage mechanism. It is much cheaper than almost any other system that I have seen. So certainly cheaper than hydrogen. Like
they've adopted this in Europe, or it's had low adoption.
There are a couple showing up in Europe right now. Again, we're on the sort of leading edge of this right now, but they are starting to show up. There's one deployed in California. There's one deployed in New York. There's a couple ones that are based on sand that have been deployed in Europe as well, even like 10 years ago. And so there are a number of different ways that people are looking at this. And when we get, there's one more slide, and I'll show you all the companies that I've found that are working on this. There are a tremendous large number of companies that are trying to figure this out, because it is, like I said, it's cool. It'd be really fun if it could get figured out and work. Looking at Texas for 2023, if you wanted a 24-hour strip of electricity, it's $49 a megawatt hour. If you selectively chose the cheapest 5 hours, it's $12 a megawatt hour. And so you are dropping prices by 75% by, again, just grabbing those cheap hours. So that's equivalent to 29 cents a therm natural gas, significantly cheaper than natural gas is currently. So there is an ROI on this project. CapEx is still real. It's still expensive. I can't work our way around that. But it is a way to, again, fully decarbonize your thermal operations, and it's pretty cool. Like I said, there's a ton of companies that are working on this. As I talked about Rondo, that's whose diagram that is. Bren Miller has one of those in New York. There's a number, as well as a number in Europe. And Tora is trying to do this, but also do electrical generation as well, which is cool. There's a lot of people working on this, trying to make it work. We'll see who wins, right? Exowatt is one of the newer ones. They have a ton of money that they got from some of the AI folks. They're sort of a data center focused approach. We'll see. So they are trying to make electricity from it. I mean, you know, it's interesting as you think about this from a different energy storage mechanisms, right? They're putting it back into heat and then turning it back to electricity. There's a bunch of different ways people are trying to crack that nut. The design perspective, this is a pretty similar approach to the heat pump. You can remove your natural gas boilers or leave them as necessary, install your hot rocks, and then schedule it to charge again for those cheapest hours on the day ahead market. And so every day they publish what the prices are going to be tomorrow, and you work with your retailer to bid in on those on that market to grab those cheapest prices. And then once you got that, you can figure out your charging process and then grab your additional renewables to support your decarb claims.
Is anyone working on cold rocks? Refrigerate those rocks for the data centers.
Yeah, no, there's plenty of ice storage companies and things like that that have been working on something similar. So, you know, thermal storage is not a new concept. And, you know, I think it's always surprised me that I think cold storage has not taken off more. We see it, we do see it from time to time, but it's not as prevalent, you know, particularly for these diurnal environments where you would think it'd be really cheap to make cooling overnight. I don't know. I think we should do more of it. All right, so strengths, very flexible demand, can fully replace natural gas today, and has a large amount of storage, which is pretty cool. Early commercialization weaknesses, like I said, really large electrical infrastructure requirements. And we don't have a lot of areas where tariffs and utility rates are really supportive for this implementation. Opportunities. I think if utilities kind of understood the value that could be associated with deployable loads, they could get on board. I think particularly as we start seeing more and more renewables showing up, I think there's a huge opportunity again for just grid resilience and grid quality. So I would encourage utilities to figure out how to get on board with these kind of concepts. And we do see that on the EV side to a certain extent, and I think there's some opportunities for more of that in some of these other operations like thermal processes. Similarly, flexible load interconnection. Again, I don't want to spend 30 minutes on this, but when you ask for interconnection from a utility, they assume you're going to be using energy at the worst possible time for them. There need to be more opportunities for a flexible load interconnection where you promise to not use electricity during those times. We're starting to see some like PG&E out in California has one. Texas is starting to do one. Speed to power is going to be really important for both this process, but also for data centers and things like that. And so flexibility, I think, again, really paramount in all of this stuff. The threat I would mention here, broadly, if the pace of renewables is as fast as load growth, we're going to have these really cheap hours of electricity. If renewables slows down and load growth increases, we may have some challenges where these prices don't go as low, and we don't get the benefits of this flexibility to really grab those really low cost hours. And that would be problematic from making this work. Any questions on hot rocks?
Why not heat pumps? I'm guessing the temperature is too high to get there.
Correct.
And how about a hybrid?
Sorry?
How about a hybrid heat pump partway? And
yeah, there are definitely some people that are looking at hybrid solutions. I think there are different ways to crack that nut. Again, you know, it's all about how do you get the volume of energy you need, and most have done it by really high temperatures and using that as sort of your storage mechanism. But you can get bigger and bigger volumes if that works for you. You know, I know there's a lot of talk about phase change materials for residential operations and things like that. could also be potentially something that works. But broadly, the nice thing about resistance heating is it doesn't care what temperature you're at for the most part, and you can just kind of keep pumping energy in and keep getting higher and higher temperatures. When you do a refrigeration system, obviously that doesn't work in the same way.
We're talking again about these data centers. So they're giving off all this heat, and you use the heat and you make electricity. And theoretically, you put it into a heat pump, right, or something for that electricity. That way, then you're cooling the data center that way. So that's kind of the loop you're talking about.
Yeah, I definitely. I mean,
because he was talking about having cool rocks.
No, totally.
Which would be more cost effective because it seems like the heat pump would be cheaper.
Yeah. I think it's it's always interesting to me because data center heat is relatively low grade, right? It's 80, 90 degrees Fahrenheit. It's not really all that useful from an industrial process perspective. It's very useful for heating buildings and things like that. And so I think there's been a big challenge on how do we integrate data center waste heat into something useful. And I think, a lot of facilities that are doing that either use heat recovery chillers or dump it into a sort of neutral temperature water loop that then is used by heat pumps. So I think there's a lot of solutions for that if you can figure out integration, right? And I think integration is really great and important for efficiency standpoint. My only caution about that is that there's only so many engineers out there who are doing this kind of work. And if we spend all of our time doing engineering work to get these things, these really great efficiency, grab this heat from over here and then plumb it over here, there's a challenge of how do we scale that in a way that we need to, right? And I think one of the great things we've seen from solar is that the growth of solar is from modularization and from not asking a lot of questions, right? And not doing a lot of design. We just have solar panels, we stick them where they need to go, and they do their thing. I think there are lessons to be learned from that across the energy transition space. And part of why I kind of like a lot of stuff that we're talking about is that this is on the supply side. I don't care a whole lot what you're doing with your steam. I do to a certain extent. But if I can go in and replace your boilers with an electric boiler or an electric system and walk away and have decarbonized your system, it may not be the 100% most efficient system, but if it's done and relatively cheap and relatively quick, there's a lot of value for that. And I think as we think about how to do some of these things and how we look forward in the sort of process of the energy transition, I think it's worth kind of trying to figure out how to actually move things as quickly as we possibly can. Sorry, I went on a tangent.
So keep it simple. In other words,
simple. No, exactly. And it hurts me from an energy efficiency standpoint, and an energy efficiency love that I initially had is that things can be inefficient, right? If we have excess renewables on the grid, we can do stupid things with them, and that's okay. As long as we're doing them only during the excess renewables times, we can do stupid things, and it will be just fine. The second we start doing stupid things during peak times, it becomes more of a problem. And I think that's how in my mind, how my evolution and my journey has led me to there. But I think there's room for everyone who has beautiful efficiencies in mind, as well as I think kind of more raw, get it done as fast as we possibly can kind of mindsets. I'll keep going here. This is my last kind of concept here. And this is I'm not gonna say lowly electric boiler, but it's the most, I would say, mature technology that we're going to talk about. Electric boilers have existed for many, many years. They're not first of a kind in any way. You can go buy one from a number of different manufacturers, including manufacturers that your facilities team will have heard of, which is always a nice thing. And so you can buy an electric boiler from Cleaver Brooks. You can buy one from Fulton. Fulton's got a cool dual fuel source one where you can do natural gas or electricity. So that's really nice from not having to use different boilers and cool one down and heat one up, which creates a lot of heartache for facilities teams for real reasons. So again, these are COPs of 1. So these are, I would say, the stupid way to use electricity. But again, if we can use it during the right times when we have excess renewables on the grid, that's okay. Because they're COP of 1, right? We're not doing anything great with electricity. We're using it in really the most rudimentary way to generate heat, like we do with a toaster, like we do with all these other things. But if we, instead of using it, I think in a more advanced way of using a heat pump, but our CapEx is going to be lower. We're going to be able to deploy these quickly in a way that I think is perhaps more acceptable to facilities teams at this point. So I've come around, quite frankly, to a lot of this concept. But again, it all fundamentally comes down to, can we access cheap electricity just like it does for the hot rocks solution? So in Wisconsin, I was looking at this. 64% of the hours in Wisconsin in Madison, we could operate the electric boiler at a cheaper cost than it would cost to operate the natural gas boiler. So that was really cool. And that assumes we could avoid the transmission charges. So caveat, they don't know when peak hour is for the transmission company. So they couldn't tell us when that might be or when it could be or give us any predictions for that. So avoiding transmission charges for this might be hard. The other thing is that they only said they would give us this contract for 5 years where we would basically be able to access that wholesale market rate. And so after that 5 years, we'd roll back on to the more expensive sort of traditional rates. Again, that would assume that we are using expensive electricity. And in doing so, it sort of destroy the economics of the system. And so that kind of blew up on me, and I got pretty upset, frankly, that I was really excited by this thing that I thought was going to work, and then didn't work because there was only a time-limited duration for this contract. And so, again, preview, one of my issues is how do we get utilities to provide some of this transparency, some of this clearance to get these wholesale market rates. When we do have market signals that are telling us use more energy during these times, how do we incentivize those economics to pass through in a way that makes sense for everybody? So if we have an electric boiler, again, we're trying to grab that cheap electricity. So we're going to do energy efficiency. We're going to maintain our natural gas boilers because we're going to use the natural gas boilers when prices get expensive or when the grid gets dirty, or when transmission constraints happen. We're going to keep that natural gas so we can basically arbitrage between different fuel sources. We're going to use our electric boilers and then operate them when those hourly prices are cheaper than the natural gas price would be. One of the other nice things about optionality on this perspective is that if our corporate decarbonization strategy needs a little bump, we can use a little bit higher prices and run our electric boiler a little bit more often, and use RECs to support that scope 2 decarbonization. So there's some nice kind of convenience there as well. But this is ultimately a very hybrid solution. It's not going to take you to full decarbonization today, but does present an opportunity to do so over time, particularly locking in that electrical interconnection load, because I think that's going to be hugely valuable moving forward, because I think that may become harder and harder to get over time. So I think this is mostly the last slide, almost the last slide. So strengths, mature technology. This hybrid approach has the chance to sort of really arbitrage those rates and those prices to get as cheap an operating cost as we can. Our weaknesses are very similar to the hot rock system, where we have limited places where this actually works, and you will bang your head into the wall trying to find those places like I have. And there is an operational, I think, challenge of what do we do with the natural gas boilers if we're asking them to operate every other hour while we use the electric boiler between. The opportunities are very similar with utility support on how do utilities support this. And the threats, I think, again, are similar to on the renewable standpoint, but I want to highlight one other thing is that natural gas availability is something that I don't think we talk a whole lot about broadly, but natural gas is being asked to do more and more during these peak hours, because essentially they're not being utilized during hours that have a lot of renewables, but are being asked to do both thermal loads in houses and commercial and industrial buildings, but also generation during again, these peak hours where there are not renewables on the grid. So I do think we are going to start seeing some more challenges on natural gas availability. So just highlight that as one other concept of that could potentially blow this concept. Any questions before I go to my summary page?
So the duck curve may start to creep into natural gas pressure.
I think so. I mean, I think the more that I have at least gone into this and understanding what the grid has to do and what we're asking the grid to do and asking natural gas operators to do, it's not negligible. And to a certain extent, I understand their frustration by the energy transition. And so I understand a little bit of their anger that sometimes shows up on LinkedIn and other places. But I do think there are ways to make it work in a simpatico way. And frankly, renewables are pushing natural gas out, and that's just the way it's going to be. And that's obviously the end duration of where we're going, right? And so as we do that, there are going to be pains throughout that process, and that's hard for them, and I understand that, but it's going to be painful, and there are going to be hiccups, I think, as we do that. All right, so closing takeaways. A decarbonized steam system is possible. So if your client or your facility is looking at removing steam to go to hot water heat pumps, I might take a second. Think about if that's truly necessary and the right approach. Again, I'm really focusing on the capital perspective. If you are going to use $1.8 billion, is this the best possible use of your decarbonization budget? Or if you spent $1.5 billion on renewables and $300 million on a new steam system, would that provide you a better decarbonization solution? And the second one is that market signals are being lost, right? Market signals on the wholesale market are very, very clear. There is very cheap electricity for a lot of the time. As I've gone through and trying to help my clients access that electricity and that cheap electricity, it's very hard to actually do in most places. And so I think it's worth considering how do utilities and how do PUCs and how do regulators think about what the actual value of some of this incremental energy is during these timeframes? And are there rate structures and tariffs and things that we can put in place that are going to support doing stupid things with electricity when no one else wants it? Because I think that's going to unlock a lot of really interesting things for grid integration and grid resilience. I think we see this on a lot of demand response and demand side management programs, but how do we unlock that for a broader swath of technologies and solutions that are not maybe fully integrated into the utility DSM programs currently? So that's my conclusion. Thank you. QR code will go to my LinkedIn if you wanna LinkedIn me, or feel free to drop me an email. Definitely this has been an area of passion of mine for a while, so love thinking about it and talking about it. I would certainly love to discuss further either tonight or in the future.
Well, thank you, Blair, and thank you all for coming this evening. I think that's it. Have a good night.